So to demonstrate the power of the Green's function method, I'll solve a problem, a slightly advanced problem, but a very important problem. It shows how the Green's function method can be used to solve a host of realistic problems. The Green's function, we have found several Green's function. We have found a Green's function for stresses, for half plane problems. We have found Green's function for displacements, for a 3D problem with a point load applied at the origin. We have found for a 2D problem the stress Green's function for a point load applied at the origin. You can find Green's function for several other problems, but now we will demonstrate a problem that was solved by Eshelby in 1957, and several other works very soon thereafter, where he solves the problem of a particle, an ellipsoidal particle, which is denoted here by omega. This is the particle here. This is the ellipsoidal particle, which has a stiffnessCijklp, which is different from that of the infinite matrixCijkl in which it sits. And this infinite matrix is supported on delta U, and tractions T bar are applied at delta Vt. Okay, so obviously if this particle was not there, the stresses would have been uniform throughout this infinite solid. But since the particle is there, there would be a disturbance of the stresses around the particle, and it was his intention to find the amount of disturbance, amount of non-uniformity in stresses that results due to the presence of a particle, ellipsoidal particle, in an otherwise infinite matrix. Now, he used a concept of eigenstrains, and eigenstrains are defined as stress-free strains, and the most logical expression, or the most common example of eigenstrain is a thermal strain. Imagine that this particle has a thermal expansion coefficient of alpha, and the matrix has alpha equal to 0. Then if you heat the whole assembly through delta T, then this particle would like to expand with a strain which I'll call epsilon ij t equal to alpha delta ij into delta T. So this would be the strain that would result if the particle were able to expand without any obstruction from the rest of the infinite body. So this, if it could have gone through this strain, there would be no stresses generated in the particle. This would be a stress-free strain. Thermal strains would be, thermal expansion is completely stress-free. There's a change in shape of the body, but there are no stresses generated due to it. The stresses are generated because the rest of the body prevents this free expansion from happening, and this causes the stresses. So these causes stresses both inside the particle as well as outside the particle. Now eigenstrains can happen, eigenstrains or stressless strains, stress-free strains can happen due to other reasons also. For example, the particle may undergo a phase transformation. Particle may undergo a phase transformation in which its volume increases, and it may change from one crystal structure to another crystal structure due to some reason. Its volume changes from one crystal structure to another. Then this increase in volume will be again stress-free if it is not constrained. If it is constrained, stresses would be generated, and Eshelby wanted to solve this problem for an ellipsoidal particle. So what he brilliantly realized is that this problem of he realized that this problem of an ellipsoidal particle sitting in an infinite matrix with a different stiffnessCijklp from that of the matrix can be replaced by a problem where the whole body has the stiffnessCijkl, same as that of the matrix, and the region of the particle is subjected to a eigenstrain epsilon ij star, which is constant inside the particle. So having a particle inside a matrix and subjecting the matrix to some external loads is same as taking a particle free matrix and then replacing the particle by a constant eigenstrain. So he then derived the solution for strains inside the particle, which is called the interior solution, strains inside the particle, which is called the interior solution, and showed that for a constant eigenstrain, the strains inside the particle, as long as the particle is ellipsoidal, is constant. And he also found the solution exterior to the particle, which he called the exterior solution, of course, that is not constant, but remarkably, the strains inside the particle for an ellipsoidal particle are constant and is independent of the properties of the particle. It's dependent only on the properties of the matrix. So just let me summarize what Eshelby said. Eshelby said that this problem of an ellipsoidal particle omega sitting in a matrix V, where the particle has a different stiffness from that of the matrix, is equivalent to a problem with the same stiffness as that of the matrix throughout, but a constant eigenstrain imposed on the particle domain. So what that means is it's like this particle has been given a thermal expansion, expanded by epsilon ij star, which is constant over the particle. Then tractions have been applied on its boundary, squeezed it down to the size that it had before the expansion, and fitted again back into the solid. When it's fitted back into the solid, obviously it will try to expand back again and therefore create stresses and strains in the solid as well as in itself. But then Eshelby showed that the strains that would be created by this attempt of the particle to expand back will also be constant inside the ellipsoidal domain of the particle, but would be varying outside. So this is the problem that we are going to demonstrate and show how Eshelby got the solution and what the solution actually means. This is a very important solution in the field of micromechanics, which is basically the science of finding out properties of composites which are formed by different phases of material. So multi-phase materials, multi-component materials, and in studies of micromechanics, Eshelby's solution forms a very, very important cornerstone. Now, to solve Eshelby's solution, to go through Eshelby's solution, we are going to use the method of Green's function, and we are going to derive the idea of Green's function from sort of the first principles. We will go make the assumptions later, but first we will look at the nature of the strains. So if you look at nature of the strain, so strain now has two parts. One is like the eigenstrain, which is kind of your thermal expansion, which is stressless, which doesn't cause any stresses, but causes a change in shape of the particle. Okay, so we call that eigenstrain epsilon ij star. This is stressless. And then there's a mechanical part of the strain which causes stresses. And the total strain is composed of the sum of these two. So this is like the thermal strain plus the mechanical strain making up the total strain. So the strain that causes stresses So the strains that cause stresses and the one that will go into the constitutive equation is actually the total strain epsilon ij minus the eigenstrain epsilon ij star. So this is your mechanical strain that will go into your constitutive equations and cause stresses. Okay, so we will work with this, put it back into the constitutive equation, and the constitutive equation in our case, of course, is for the elastic case is sigma ij equal to c ij kl epsilon kl, but this epsilon kl now is the epsilon kl m, and therefore we'll have to replace it by c ij kl epsilon kl minus epsilon kl star. So this is our constitutive equation in the case where we have eigenstrain imposed on part of the domain, part of the material. So now we know that in absence of body forces, sigma ij comma j is equal to 0. So I can take derivatives on both sides, sigma ij comma j, epsilon kl comma j, epsilon kl star comma j, and epsilon kl comma j is, so epsilon kl we know is half u k comma l plus u l comma k. So epsilon kl comma j would be half u k comma lj plus u l comma kj. Okay, so now when you multiply with c I j k l, so you multiply this with u k comma lj plus u l comma kj, you will see that c I j k l has a few symmetries that we all know. So c I j k l is same as c j I k l, is same as lk, and c k l I j. So it has these symmetries that we know already. If you make use of these symmetries, and I leave this exercise to you, you can show that this is same as what you have here. So k comma lj, Cij kl u k comma lj is same as Cij kl u l comma kj, and both of them together give you 2 times the first term, and then this half cancels the 2 out and you get this. And here I have Cij kl times epsilon kl star comma j is equal to 0. Okay, so this is kind of your Navier's equation. This is kind of your Navier's equation, but in Navier's equation we use the isotropic form of Cij kl. Here we have not used the isotropic form yet. We are keeping it general. So this is what we have now. This is the governing equation for a problem without body forces subjected to eigenstrains. Now take Fourier transforms on both sides. Again, we are taking now 3-dimensional Fourier transforms. So uk comma lj would be uk bar zeta l I times zeta l into I times zeta j. So that would lead to minus zeta l zeta j uk bar. Plug that in here. This is what we have, and on this side you will have epsilon kl star bar, and because of this j you will have I zeta j. So that would lead to, if you take Fourier transform of both sides, you will get this expression. Okay, now we will define this part to be aik, and aik we have encountered before. This is called the acoustic tensor, and aik is dependent on zeta l and zeta j, so it's dependent on zetas. So this is a function of zeta, the Fourier variables, zeta 1, zeta 2, zeta 3. The right hand side, this whole thing, we will call it xi. So xi is equal to this whole quantity here. So now you have this, which is a 3 cross 3 matrix. 3 cross 3 matrix. This is a 3 cross 1 and this is also a 3 cross 1 vector. So you can now invert aik to get uk bar, and once you have got uk bar, you have the inverse Fourier transforms to get uk out of it. Now obviously in all cases, remember that aik is a function of zeta. Inverting it would be like inverting a bunch of functions in zeta. You can invert it, invert a 3 cross 3 matrix by the usual method. And the usual method involves the following. When you want to find A inverse, the way you would do it, you would find the determinant of A. So you will find the determinant of A, which will be dependent on zeta because A's are dependent on zeta. And then you will find another matrix N, which is actually the cofactor matrix. Okay. So it is the cofactor matrix of A, and then you will divide by the determinant to get the inverse. This is the way we calculate inverses. So let's call the cofactor matrix as N. Both of these would be functions of zeta, of course, because the A itself is a function of zeta. So let us do the inversion in this way. And so we have this as the inverse. We have this as the inverse. So aij inverse is itself a function of zeta, which is given by d inverse, which is the determinant function of zeta again, times this cofactor matrix nij, which is also zeta. I hope you know how to form the cofactor matrix. When you invert a 3 cross 3 matrix, how to form the cofactor matrix. If you don't know, just look up a book on linear algebra, basic linear algebra. Now I'm going to use that expression here, and I am going to find ui bar. Ui bar is aij inverse xj. So I have the expression for xj. I have taken this thing to be xi. So xj would be I replaced by j and j replaced by something else. So if I do that, this is what I get for ui bar. This is what I get for ui bar. And then if I want to get ui, I do the inverse Fourier transform for 3D. That inverse Fourier transform involves 1 by 2 pi cube, and this I comes out of the integral. You have this, which is notionally something that you can solve. If you can solve this integral, you find the displacements due to an eigenstrain epsilon mn star applied on the domain just by solving this integral. That's it. Now let's go a step further, because we don't really want to solve this integral right now. What we want to do is to extract the Green's function from it. So to do that, I will replace epsilon mn star bar by its Fourier transform. So this is obviously true. Mn star bar is by definition a Fourier transform minus infinity to infinity epsilon mn e to the power minus I zeta dot x dx. So this is by definition. I am going to plug this in, but I already have this x here, so I'll call this y dy, and I will plug this into this, and I have now two integrals going from minus infinity to infinity. One because I replaced epsilon mn bar star by this exponential, and this is what I replaced it by, and the other was already there because I have taken the inverse Fourier transform. Now you have the zeta L here. Okay, now I can get rid of that zeta L very easily. Now look at this result. So if I take this quantity now, so this quantity is the same as what you have here except that zeta L, and take a derivative with respect to xl. If I take a derivative now with respect to xl, then x doesn't appear anywhere except here, and this quantity is zeta m xm. This is a dot product, zeta m xm, and if you take del xl of this is I zeta m xm. So if you take del xl of this, then you will get I zeta L out of it. So del xl of this quantity will give you I zeta L. X is not there anywhere else. So obviously del xl of this will be I and zeta L here, and the rest of the terms will all remain as they are. And if you look carefully, this quantity is now same as this quantity, which means that this whole integral here is del xl of this integral. Okay, so this integral does not have the zeta L. This integral does not have the zeta L because that is hidden in the del xl here. Okay, so I am going to replace this quantity with the del xl of this quantity, and the difference between these two quantities is only in the zeta L. So carefully work this out because this may not be apparent at first glance. Okay, so now let us start with this integral with everything except the epsilon mn star. And now let us define a Green's function as Gij, which is the entire integral there except for the epsilon star mn part. So this whole thing is the Green's function, and if you can evaluate this integral again, then you can get the displacement Green's function for this problem right away. Okay, so you need to obviously formulate the cofactor matrix and you need to formulate the determinant for the material, but other than that, if you can evaluate this, you get the Green's function right away. And if you take the derivative of this Green's function, that means if you get Gij comma L, okay, then you get everything in this expression, including this zeta L, So now I can write my Ui as Cjlmn epsilon mn star Gij comma L, and this you would realize is a convolution between this quantity that you have applied as eigenstrains and the derivative of the Green's function. So the displacement is a convolution between the derivative of the Green's function and the eigenstrain that you have applied, the force due to the eigenstrain, the stress due to the eigenstrain that you have applied. So C times epsilon is a stress quantity, C times epsilon star is a stress kind of quantity. So this you can think of as a stress that you have applied due to the eigenstrain, due to the expansion of the particle. This is the stress that was generated. This is the derivative of the Green's function that generates these solutions. And once we know this Green's function, we simply evaluate these integrals for any epsilon mn star. We can evaluate these integral and get this displacement distribution at any point. Now, what Eshelby said was the following, that inside that ellipsoidal domain, so he realized that this ellipsoidal domain can be represented by a similar ellipsoidal domain but with a propertyCijkl instead of Kijklp. So the stiffness inside the ellipsoidal domain is now same as that of the matrix, plus a constant eigenstrain applied inside. It is as if the ellipsoidal particle has been uniformly expanded and then fitted back into, it has been taken out of the material, expanded by epsilon star uniformly, and then you have applied forces on its boundary, reduced it in size and fitted it back into the hole from which you took it out. When you put it back into the hole, it tries to expand again, and as a result generates strains in the material as well as inside itself. So Eshelby realized that these two problems are equivalent. So you can solve the problem of an ellipsoid with propertiesCijkl P by assuming it to be of propertyCijkl plus a uniform eigenstrain inside its domain. So epsilon ij star is a constant within the domain omega for the Eshelby problem. So got the general solution for once we have got the general solution for ui, we now have to use the fact that this guy for Eshelby is a constant within omega, so and it is equal to 0 outside omega. So this integral now becomes an integral over omega only, and epsilon mn star comes out of the integral, so that we now have a simpler integral to evaluate. Also, Cjlmn is a constant, so it also comes out of the integral. And if I know this Green's function, then I can easily find the solution to ui. Now, to know the Green's function, I have to evaluate this integral. And to evaluate this integral, the most important hurdles are finding the cofactor matrix and the determinant. To find the cofactor matrix and the determinant, what we will have to do is we will have to find the inverse of the acoustic matrix. So this is the acoustic tensor, and we will have to find its inverse. The finding its inverse is difficult for a general case, but for the situation whereCijkl is isotropic, for an isotropic material, we have already seen how to find aik and how to find aik inverse. In a previous problem, we have seen how to find aik inverse. We'll use the same trick here, and aik inverse for an isotropic material can easily be found. We can replace it here and find the Gijkl to be this, which is same as what we had found earlier. Remember, r square is xk and r comma l is xl by r. So using that, you can verify that our previous expression for Gij that we had found as the first problem in the Fourier transform application of Fourier transforms, the first problem, we had found a similar expression for a load pi applied at the origin, and this Gij is for a unit load applied at the origin. So it's the displacement at a point x in the direction I due to a load applied in the direction of j at the origin, due to the component of load applied in the direction j at the origin. That is what is physically given by your Gijkl. Given by your Gij. Okay, so this is the Gij for an isotropic material, which is obtained by evaluating this integral with Nij d inverse for an isotropic material. Once you have done that, you take its derivative, plug it into here, and you find the ui. Okay, it may still be complicated. So in Eshelby's scheme of things, omega is the ellipsoidal particle. So an ellipse has major and semi-minor axis, half major and semi-minor axis of A, B, and C. So this is the domain over which epsilon star is non-zero. Everywhere else it is equal to 0, and the C and the epsilon are constants, so they come out of the integral. So this is the only part of the integral that you need to evaluate over this domain omega, where Gij for isotropic cases is given by this expression. So you have to take its derivative and a derivative with respect to xl, and then perform the integration. The integration may not be easy, but Eshelby again in a remarkable result showed that this would uh, constitute, so if you take this epsilon I and calculate the epsilon ij, which again would be a function of x, then you can express it as Sij epsilon kl star, where this Sij is a constant tensor called the Eshelby tensor. Remember, this is constant within the particle and zero elsewhere, which means that this inside the particle is now a constant. So this particle, as long as it is ellipsoidal and is sitting in an elastic matrix, is actually subjected, after it has been fitted back into the hole, after imparting epsilon star, it has been fitted back into the hole, and after being fitted back into the hole, inside the particle, the strain is a constant if the particle is ellipsoidal in shape. So that is Eshelby's main result. The tensor Sij has been tabulated for many shapes of particles, many ellipsoidal particles, and it does not depend on the properties of the particle. It depends only on the properties of the matrix. Okay, and for example, for spherical particles, when A is equal to B equal to C, these are the simple expressions for S, which depend on only nu of the Poisson's ratio of of the matrix. So it does not depend on the properties of the particle at all. So what Eshelby basically showed is that if you take an ellipsoidal particle which is sitting inside a matrix out of the matrix, leaving a hole in the matrix, then impart a epsilon star, so the particle grows in size or shrinks in size, and then you sort of apply tractions on the boundary of the particle to bring it back to its original shape and fix it inside that hole. Just perform this thought experiment. You fitted it back into the hole in the matrix, then it creates a stress field around itself, and it creates a stress field inside itself, because the rest of the material does not like it be applying these tractions on it. So when it does that, the strains and therefore the stresses inside the ellipsoidal domain remain constant. That is the major result, and this constant strain depends on, of course, how much eigenstrain you have applied, but also on the properties of the matrix. It does not depend on the properties of the particle. This is the most important result for Eshelby's case, and for spherical particle, these are the results.